So let's do another problem here. Let's say that we have a pendulum hanging on a length here, and it is initially, we'll call this, mass M, okay, and let's say it's initially at an angle of 40.0 degrees. Let's say that L is a length of 125 centimeters. Let's say that the mass is going to be 650 grams. Now, when you let go, it swings down here and it hits a little smaller mass that was sitting there. And then afterwards, it swings up over here with that little smaller mass stuck on it. So I want to know how far up does it swing. So you need to know what the small mass is. So let's say the small mass is 250 grams. Okay, so what's going on here? Well, we've got several problems happening. First of all, in the collision process down here, momentum before the collision equals momentum after the collision. But momentum is mass times velocity, so we need to know the velocity before the collision and the velocity after the collision. So the velocity before the collision comes from this thing swinging. Swinging downward is conservation of energy. So this is actually a little bit more complicated problem because we have to solve this problem in three parts. Before the collision, during the collision, and after the collision. Before the collision, this is a conservation of energy problem. During the collision, conservation of momentum. After the collision, it's swinging again, so conservation of energy. So we have three parts of this problem that we need to deal with. So first part, before the collision, the object swings down to the bottom and we want to know how fast is it moving. Okay, so we've done this problem before. So here's, theta naught, okay, and so we would say it's conservation of energy, so K sub I plus U sub I equals K sub F plus U sub F. If I put my height 0 at the bottom, U sub F is 0. We release from rest, so K sub I is 0. So mgh equals 1/2 mv squared. The m's cancel, so v is square root of 2gh. Well, how far is h? H is this height right here. Okay, and so how do we find that? We know the total height here is L, and this little piece right here is going to be that's going to be L cosine theta. So H is going to be L minus L cosine theta, or L times 1 minus cosine theta. So that means that V is going to be the square root of 2gL1 minus cosine theta. So the velocity is going to be, if you work all that out, 2.39 meters per second. So that's the velocity right before impact. Now, part 2, impact. So we have this mass here, big M, it's hitting the small mass, little m. So it's coming in, hitting, and then afterwards the two are moving together. So afterwards it's big M plus little m moving together. So now we have this initial velocity right here and the final velocity, the two moving together. So initial momentum equals final momentum. So that means we have m times v initial equals m plus m times v final. Okay, so that means that we can then say v final equals mv initial divided by m plus m. Well, we know all these m's, so we plug in the numbers, And so the V final is 1.73 meters per second. Okay. Now, after the collision, they swing up here some distance, theta final here. Okay. And so what do we have here? Well, it's swinging motion again. So only thing acting on it is gravity. So K sub I plus U sub I equals K sub F plus U sub F. Okay, so if I put my origin, the bottom down here, that's 0. It stops when it reaches the top. And so we know that 1/2 total mass times V squared equals mass times G times H. Masses cancel. Okay, so H, the height, turns out to be V squared over 2G. Okay, so we've got that. Well, then wait a minute. What is the height? Well, the height is the same thing. It's L times 1 minus cosine theta. So what we have here is L times 1 minus cosine theta equals V squared over 2G. So 1 minus cosine theta equals V squared over 2GL. Okay. That means that cosine theta is going to equal 1 minus V squared over 2GL. So theta is the inverse cosine of 1 minus V squared over 2GL. Now I can plug in all the numbers and you get 28.6 degrees. We started off here with this mass M, swung down, hit a small mass, swung up over here with a small mass sticking to it. It was originally at 40 degrees. It ended up at 28.6 degrees. Okay, and that's because of this complex sort of system right here, where in the middle we had collision. So conservation of energy, then the collision is conservation of momentum, and then conservation of energy afterwards. So this is a swinging pendulum, swinging and hitting something. And so that's an example of how you would use conservation of energy and conservation of momentum in the same kind of a problem.